Hello, this is the start of chapter 11, which is talking about phase diagrams. We skipped chapter 10, which is about failure, fracture, fatigues, item like fracture, fatigue, and creep, because this part can be discussed in the in mechanics of material. We are following, or we are addressing the following items. We'll talk about when we combine two elements, what is the resulting equilibrium state. We'll talk about what do we mean by phase. In particular, we specify if the composition, for example, is a certain value. We can specify it, or we learn how to specify it when the temperature is known. Then we look at how many phases are formed and what is the composition of each phase and the amount of each phase, how much or what is the amount of each phase. The first term that we should discuss it is phase. In a simple description, phase is a region of material that is physically distinct, that is chemically uniform, and in most of the times it can be mechanically separated. The other term is solution. Solution can be in form of solid, liquid, or gas solution, and it can be single phase, of course. When we have more than one phase, it's called mixture. The maximum concentration for which only a single phase solution exists is called solubility limit, as you can see here. So you can see the temperatures versus composition of a certain material. Here we have solution of sugar and water, what we know as phase diagram. Here on the left side we have liquid solution. Then we have the boundary, and then we have, if we add the sugar, of course we will have combination of liquid phase and the solid phase, which is the sugar. We want to calculate it. We want to know what is the solubility limit for sugar in water at 20 degrees Celsius. So we can easily go to temperature degrees Celsius, go from 20, so that we reach to the solubility limit boundary, and then go down and we find the value here. As you can see here, the composition, the value that is the solubility limit for 20 degree is 65%. Of course, at 20 degree, if the composition is below 60, we deal with the syrup or water sugar, and if it's above that, we have two phases of liquid and solid sugar. In this chapter, do not mix what we talk about phases and components. When we say components, we mean the elements or compounds which are present in alloy. For example, we have aluminium and copper, or so on and so forth. So we talk about those components or those elements that are ready. And if we have a physically and chemically distinct material regions, that forms the phases. As an example, you see here the lighter phase is beta phase and the darker one is alpha phase. In both of them we have compounds of aluminum and copper. Now look at here at this system and at this chart. Here we want to show different phases and different states of sugar water system at different temperature versus different composition. It's very similar in the previous slides that we showed there. We want to see what altering temperature can cause in the system. As you can see, raising temperature from point A to point 2 actually changes the number or the type of phases from A to B. At A, the temperature is 20 degree, the composition is 70. At B, we have the same composition but higher temperature. And regarding the composition, Of course, altering composition can also change the number of type of phase. As you can see, we have one phase here, and if we increase the composition percent from 70 at point B to 90 at point D, then we have two phases. Bear in mind that the chart, we will have this chart in case one system or one component like sugar can be soluble in the other component. And just go back to chapter 4, what we talked about, criteria for solid solubility. As an example, in nickel copper solution, because we have both type of same type of crystal structure in both of them, very close value of electronegativity, and are to a very similar and close value of their atomic radii, then of course we can conclude that based on Hume-Rothery rules, we could conclude that there is high mutual solubility between these two atoms, so we expect Ni and Cu to be soluble totally in one another for all proportions. The chart, like this chart that talks about CuNi system, copper nickel system, that shows different phases occur and exist at different conditions such as temperature, pressure. In terms of the weight percent and composition of the other one of one of the elements, this chart is called phase diagram. It indicates phases as a function of temperature, composition, and pressure, in simple word. For this course, as we have two components, Cu and Ni, we call it binary system, and the independent variables are temperature here and composition on the horizontal axis. The pressure is almost always the 1 atmosphere is assumed or used. As you can see, we have two distinct phases, liquid and alpha solid solution phase, and we have three different phase fields. One is only liquid, this one is only alpha solid, and this one is combination of both of them. So in this phase diagram, as we are dealing with two components, Cu and Ny, it's a binary system, and because there is complete solubility of one component in another, alpha phase field extends from 0 to 100, then it is also isomorphous. In isomorphous phase diagram, we have complete range of one component from 0% to 100% on the composition axis. In phase diagram, as the first rule, if we know the value of temperature and composition percent, then we know which phase or phases are present in the phase diagram. As an example, at point A, that we know the temperature is 1100 degrees Celsius, and the weight percent of nickel is 60%. Of course, we are dealing with one phase, which is alpha solidus, and at point B, in which the temperature is 1250 degrees Celsius and weight percent of nickel is 35, we are dealing with two phases, which is the liquid plus alpha phase. The second rule in the determination of phase composition tells that if we know temperature and the composition, then we can determine the composition of each of these phases. As an example, consider a composition of 35% at temperature A here, which is 1320 degrees Celsius. We only have liquid phase, and the composition of the liquid phase is same as the composition we have here, with 35 weight percent of nickel. If we go to D, we only have only one solid alpha phase, as you can see here at point D, and C alpha. The composition in the solid phase is the same as composition in this point with a weight percent of 35. But at point B we have both phases present. Point B, which is at about 1250 degrees Celsius, we have both alpha phase and liquid present. So the value of Cl, of composition of the liquid, can be found using this tie-line system. The composition of the liquid system, we just go horizontal until it intersects with the border of liquid and alpha phase. Therefore the composition of liquid is, as you can see, 32 weight percent of nickel, and the composition of the alpha phase can be found from this line going horizontal, and the intercept goes down, which is 43 weight percent of nickel. In other words, at point B we have the liquid phase at which the composition of nickel is 32%, and we have a solid phase alpha at which the composition or the weight percent of nickel is 43%. Now we go to the third rule, which says that if we know temperature, the vertical axis, and C0, the composition in the horizontal axis, then we can determine the weight fraction. So far we were talking about the composition percent. Now we can also determine the weight fraction of each phase. As an example, if you consider C0 equal to 35%, of course at A we only deal with one phase liquid, therefore the weight fraction of liquid is 1 and alpha is 0. No, their total number should be 1 or 100%. If we go down to point D, we only deal with solids with alpha, therefore the weight fraction of alpha is 1 and the weight fraction of liquid, there is no liquid, of course it's 0. What about point B, which is in the part that we have two phases, L and alpha? In order to find the weight fraction of liquid part, of course if we are dealing with this point exactly here, the weight fraction of liquid should be 100% liquid, 0% alpha. If you go to the right, the weight fraction for liquid should be 0 and the weight fraction for alpha should be 1. In the middle, of course, we have to find this relation. The weight fraction of liquid is found from the S, distance from the solidus part to the desired point in the tie line, divided by their addition. Of course, the bigger S, we go to the left side and we have more liquid. And in order to find the alpha phase, we use the fraction of R divided by their summation. Of course, if you go from left to right, the R increases from 0 to the maximum value, and here of course we only have R divided by R, which gives us 1 for the weight fraction of alpha. Here it gives 0 for alpha. For B, which is in the middle, of course we can find this distance by deducting the composition percent of alpha from this point. So it's 43 minus 35 divided by their summation. So this value gonna be 43 minus 35, and their summation is from this point here all the way to the solid part. So it's gonna be 43 minus 32. This gives 73% of weight fraction for the liquid phase. The same we can calculate a 27% weight fraction for alpha. The relation that we just use is known as the lever rule. If you look at this phase diagram, and when we are looking in the region that we are dealing with two phases at the same time, at a certain point like B, this is if we want to find the fraction of each phase, we actually use like a teeter-totter or a seesaw, and you can imagine that the mass of solid part is here, the mass of liquid part is here. Of course, with these two arms, we can write down this relation: m alpha times the arm is equal ml times r. This is the same as like moment that is applied on the both sides of this lever. So from here we can write down also that the weight of liquid part, the weight fraction of liquid part, is equal to the liquid mass divided by the total mass. We can take ml out from the lower part of the fraction, so we will have 1 plus this fraction, and instead of so ml from up and down are cancelled, and then we are ended to this relation 1 over 1 plus rs, which can be simplified to this relation: s divided by s plus r, and s is this distance is shown here, which is equal to c alpha minus c0, and the total distance is equal to c alpha minus cl. So this is for the weight percent of liquid, and then for alpha we can do the same type of calculation, which ends with this relation. This is known as a lever rule. Also bear in mind that the tie line that we have here is actually connecting the phases in equilibrium with each other. Also sometimes this tie line is also called isotherm, because it's happening in the same temperature. Now consider that we are starting from a single phase like this liquid, and we cool down the composition of our system, which is here copper nickel system, and we want to see what is happening in the microstructural morphology of the system when we cool it down. So we want to look at the microstructural changes at this point. This point is actually corresponds to composition weight percent of 35% of nickel alloy. So at A we are expecting a liquid, whole liquid, and the weight percent of nickel is, the composition percent is 35%. If we go down to a point like B, which is just a little bit to the right of the liquid phase, it is in these two phases. At B we actually see these two phases, and because there is a little bit of alpha phase and it's just this little here, so we are expecting tiny spots in the microstructure having alpha phase. What is the weight ratio or the composition of nickel in this alpha? We go to the right, and this value is equal to 46%. So however the weight ratio of alpha phase is very low, we have a high nickel weight ratio in this one. In the rest we have liquid phase, and the weight percent of nickel is 35 from this tie lever line. We go down a little bit to the middle of this two phase. At point C, of course we are expecting more weight ratio of alpha phase, because we are getting closer to the alpha phase. As you can see, these points are becoming larger. The green surrounding is liquid. In the liquid part we have 32 weight percent of nickel, and in the solid part we have 43% of nickel. We go down just a little bit to the left of the solidus part. Still we are dealing with two-phase material. Green is liquid with the weight ratio of nickel being 24, and 36% weight ratio of nickel. And if we go down, of course we only have the solid part, and here we already have the formation of grains, and we can see the grain boundary in the microstructure. In the same system we can also study the effect of solid solution, strengthening on tensile strength and ductility, as shown here. These are related to what we discussed in chapter 8. So here I thought it's better to remind again that phase diagram is By phase, what we mean is a homogeneous part of a material system, and when we have two metals that can added together in an alloy, if they are not completely soluble in one another, then they create different phases that can be addressed in a phase diagram. This solubility may be due to these items: atomic radius differences and different crystal structure, different electronegativity. And what happens in phase diagram, it gives which phase is present at a certain temperature and a certain value of composition. The composition is along the x-axis and temperature is normally along the y-axis. Now look at a more complex phase diagram or system. An example is a copper-silver system, because we are dealing with two components, so this system is binary, and because this system, as you can see here, it has a special composition with a minimum melting temperature here, so this is called eutectic. We will talk about the definition of eutectic more. So this is a binary eutectic system. So in this case, however, we have three different distinct phases: alpha, liquid, and beta, but because we are dealing with two components, it's called binary. We have three distinct single phases regions, as I said, and there is limited solubility. Alpha is mostly copper, beta is mostly silver. Here eutectic temperature is the temperature, the melting temperature here, which is close to 800 degrees Celsius, and there is no liquid below this temperature, the eutectic temperature. And the composition at temperature TE, or eutectic temperature, is known as C, the eutectic composition. The eutectic reaction is when we go from the liquid case here down along CE, or eutectic composition. As shown here, we have liquid at composition of CE. Of course, here now we have two phases. One of them is alpha and the other phase is beta. Alpha, the percent or the composition of silver is, or can be found from here, and the composition of beta can be found from the right side, which is written as here. For the liquid phase, just a little bit above this point, we have 71 from here, 71.9 weight percent of silver. If we cool it down, then we have 8% of we have alpha phase that has 8 weight percent of silver, plus beta phase that has 91.2% of, from here, silver. Let's have a look at this system. In this system, which is a lead tin eutectic system, again we have special composition with a minimum melting temperature. That's why it's a eutectic system, and it's lead tin. For a 40 weight percent of tin and 60 weight percent of lead alloy at 150 degrees Celsius, we want to determine the phases present. So we simply look at 40 weight percent of Sn, go up, and from 150 degree to here, and this is the point. At this point we have a combination of alpha phase and beta phase, so two phases are present here. Now we want to calculate the phase composition. Of course, we use lever rule. The phase composition for alpha, we use this tie line, the phase composition for alpha can be found from here, so it's only 11%, and the phase for beta can be found from this point, which is 99%. So here we found that the alpha phase already at this point has 11% of Sn, or tin, and the beta phase present at this point has 99% of tin. Now we want to find the relative amount of each phase. So of course now we use the lever rule. For weight percent of alpha, we use this relation S divided by the total length, and for beta we use R. So this part divided by the total length. S is 99 minus 40, R is 40 minus 11, and total length is 99 minus 11. This gives a weight percent of alpha phase equal to 67%, and weight percent of beta is 33%. As we have two present phases, of course if one of them is 0.67, the other one should be 1 minus 0.67, which we can see it's the same value that we are expecting, because the summation of these weight ratios should be 100% or 1. This question is almost similar. For 40 weight percent of tin and 60 weight percent of lead alloy. Now we want to calculate and determine the phases present at 220. So from here we go to one level up, so we will meet here, and then we want to see what are the percentage of each phase. So if we fall somewhere here, see 40% is yeah, almost here, and then 220, so they will meet here, two phases. And if you want to find the phase composition, and similar to the previous slide, the relative amount of each phase, we do a similar step. We can work